And I had started class with this problem. Factor the polynomial f of x equals, well, 4x cubed minus 8x squared minus 11x minus 3. Good luck. You would have said, I don't know what to do, okay? But I gave you a hint, right? I said, hey guys, I think this is a factor, and then you checked. And once you had one factor, you could get the rest. You guys with me? So a real issue is, can we find factors? Can we find, so equivalently, can we find zeros? Zeros geometrically are what kind of intercepts? X-intercepts. Can we find an X-intercept? So I'm going to pause for a minute and ask you, how do I know this thing has to have an X-intercept? Without a calculator, I know that this was going to happen. Oh wait, it's hard to see when I'm zoomed in. I'm going to zoom back out. I know it's going to start off negative and end up way positive. You see it going way up there high? So I knew it had to cross the x-axis at some point. Now, actually, what does this thing actually do? How many times does it cross the x-axis? Well, let me zoom in again. That's kind of weird. It hits at -1/2, but then what's it do? Boy, I guess I really got to zoom in. So let me press zoom in and let me go right over there. And let's really see what happens. Oh, does it actually cross? Hard to tell. Well, but we know because we did the problem already once that 2x plus 1 was a factor twice. So what we say is that -1/2 has multiplicity too. Multiplicity is the word. Have you seen that word? Okay, that's what it means. It means it doesn't actually cross, but it just kisses it. All right? Now, why did they say twice? Well, here, let me show you guys something. I'm going to go to the y equals screen. And instead of saying -3, I'm going to say -2. What do you think that's going to do to my graph? I was subtracting 3, but now I'm only subtracting 2. So what's going to happen to the graph? It's going to move the whole thing. We understand transformations. That's a shift by 1. So now, when I look at the graph, how does it change right around here? Well, it crosses the x-axis twice. You with me? Now, if I go back to the y equals and I say, well, it's 2.8, -2.8, and I graph, it's still going to cross, just not as much. Are you with me? And if you keep pulling it down, 2.9, etc., when you get to 3, that's when something kind of magical happens. And that is, those two x-intercepts become 1. That's what a zero of multiplicity 2 is. It means if you jiggle it a little bit, you'd have 2 zeros. You start pulling it down until they just barely touch. What Mitch was talking about today. You guys follow? Okay, now, back to this problem without a calculator. Really? Yeah. I mean, how would I have any guess where the zeros are? Okay. The first theorem is Cauchy's bound. By the way, this one was new to me. I didn't know this. Pretty cool. It tells me where I might be able to find the zeros. Okay? I just want to show you how to read it because there's an important idea contained in it. Okay? They have a polynomial written with all these n's. Oh, I can't even touch it. That's weird. Right here, you guys see the n? Right in here? Okay. So I guess my question is, that right there, that x to the n, what's n in our example? 3, because we have a third degree polynomial. Okay? So I'm going to be dividing a0 by a to the n, a1 by a to the n, a2 by a to the n. And the reason for this, I could think of this polynomial. G of x is f of x divided by 4. And it's x to the cubed minus 2x squared minus 11/4 x minus 3/4. I divided everything by 4. Okay? Now if I did that, I'm going to say two things about it. Number one, g of x has the same zeros as f. Do you agree with me on that? Because if I say 0 equals 4x cubed, etc., can you divide both sides by 4? Sure. What's 0 divided by 4? 0. So it's going to have the same zeros. So that's kind of cool. One down fact, though, g of x is ugly. It has fractions. That's the downside. So I don't really want to do what I just did for you. I don't really want to divide, but I want to think about dividing by what? 4. Because that's the, remember that was what kind of gives us the problem, is the leading coefficient. All right? Now, what I think, if you follow this rule, you can get kind of a bound on where the zeros might be. So let me read carefully what Cauchy, let me show you what that theorem says. Okay? So Cauchy's bound, you do this. We compute a number that the book calls m. Capital M. M is the maximum of the following numbers. Let's see if you follow what I'm doing here. 3/4, 11/4, 2/4. That's good. I'm sorry, it's not 2/4. It's 8/4, which equals what? 2. Where the heck did I just get those numbers from? Well, they show up in this little g. 3/4, 11/4, and 2/4. Well, 8/4, which is 2. Or, another way to say it is, I took these numbers and divided by what? Yeah, 4, which is the leading coefficient. Okay? And now, I look at that, so what's the maximum of all these numbers? 11/4, right? So m is 11/4. Okay? Well, Cauchy's bound says the zeros all lie between m plus 1 and the opposite of, well, m plus 1 in parentheses. Okay? Notice that you need absolute values. I mean, really, what I did was I took things like the absolute value of, I didn't use -3/4. I just used the positive. Okay? But Cauchy's bound says all the zeros are going to lie between here and here. So for us, let's see, what's 11/4 plus one more? Oh, you can't see, all right. Well, 15/4, right? So let's go ahead and It's 3.75, right? And what this tells me is all the zeros lie between negative 3.75 and positive 3.75. That's really a nice fact to know. And let me show you why that's important. Suppose you guys say, I'm going to use the calculator and I'm going to find the zeros. Here's a graph, right? Well, I might find negative 1/2, but guess what I'm going to do? I might miss one of the zeros. Remember that other line that's shooting up over on the right? You might not see it. So there's a button here called Window. X min and X max. What can I do now that I have Cauchy's bound? I can set X min to be what? Negative 3.75. I can set X max to be 3.75. And now when I graph, I guarantee I'll see everything. There's that last zero. Do you guys see it? There's an x-intercept over here, which ends up being, we figured it out last time. What was it? We factored the whole thing. X plus 3 was a factor, right? Or x minus 3 was a factor? X minus 3 was a factor, so 3 was the other zero. Okay? So that's how you use Cauchy's bound. Do you follow? Matt? In the theorem, if you read carefully, it says you need to use absolute values. Let me show you. Right here, all these A's, there's absolute values around everything. So even though my function has a bunch of negative numbers in it, I don't use the negative signs, okay, when you compute M. Go ahead, Mitch.
You always divide by the leading coefficient.
Yeah, because if you look at the theorem again, notice all of those things with absolute value bars, they divide by A sub n. That's your leading coefficient. If the leading coefficient's 1, it's easy. You don't even have to worry about it. Okay? Now, next thing to do is to talk about a theorem I did know about. This one to me is even more important. The rational zeros theorem. Rational. Hey, what's rational mean? Well, yeah, real's different. What kind of number is negative 1/2 rational? Yes, because it's a fraction. What kind of number have we seen recently that's irrational? Square root of 3. This isn't going to help me for square root of 3. But this theorem will help me find the rational zeros. And in this problem, they're all rational. Okay? And let me sum it up. The rational zeros theorem says zeros are of the form. Oh yeah, I'm sorry. I got the stupid book in the way. Get out of here. The rational zeros theorem says zeros are of the form plus or minus P over Q, where P divides A0 and Q divides AN. But because I don't have those A's listed, let me give you names for these things. AN is called the leading what? AN is the thing I kept dividing by. The leading coefficient. And in our example, what is AN? 4. In our example up above, AN is 4 because the original problem is there. Here, I'm going to go ahead and write it down here again so we can see it. My example, f of x is 4x cubed minus 11x squared minus 11x minus 3. That's the example I have. Okay? So AN is 4. A0, do you know what A0 is going to be? It's the constant term, yeah. So what is A0 in my example? Negative 3, that's right. negative 3. Now, here's how this works. What are the factors of 4? So here's what I'm going to say. Q could be plus or minus 1, plus or minus 2, or plus or minus 4. That's what Q could be. Because Q has to divide A sub n, the leading coefficient. The only numbers that really divide evenly into 4 are 1, 2, and 4. You guys with me? No? Well, let's see if I do the other, if I tell you what P could be, if that helps. P could be, very good, plus or minus 1, plus or minus 3. Why are there less possibilities for P than there are for Q? Yeah, because what kind of number is 3? It's a prime number, right? So you have to look at all these different factors. And now, here's what I'm going to do. I'm going to list the possible zeros. The possible zeros. Remember, they have to look like plus or minus P over Q. And you have to take every possibility into account. So watch this. The possible zeros for this problem are going to be, well, P could be 1. So I could do plus or minus 1 over 1, plus or minus 1 over 2, plus or minus 1 over 4. Because remember, Q could be 1, 2, or 4. Also, P could be what? Plus or minus 3, right? So plus or minus 3 over 1, plus or minus 3 over 2, plus or minus 3 over 4. Wow. But that's it. That's all the possible rational zeros there could be. That's it. 7 is not a 0. 15 is not a 0. But one of these things might. By the way, what were the zeros? We computed that. Yeah, we got positive 1/2. No. Negative 1/2 was a 0. Well, that's listed right here. And what else was a 0? Is positive 3 listed? Right there. So, kind of a cool little fact that can be helpful. Remember I said, is negative 1/2 a 0 or not? Well, I can tell if it's possible this way. All right, we are done. If you